last time there are some very problem. Say let's say I have a function fx versus x and it has nonlinear relationship. I have a function fx which is nonlinear with x, and if you see very carefully, let's say I fix a value of x0 here and I take a slope here at this point. So for a small variation between say x0 and x0 plus minus dx, if I see linearity maintained, then I would say the output will be proportionately linear at these points, exactly linear, therefore proportional. Equivalently saying x0 is your DC value and plus minus dx is the AC signal. So AC signal does not make VGS minus VT currents. Currents are essentially DC current, which is capital VGS minus proportional to minus VGS minus VT, around which AC signal just superimposes. Therefore, it does not change the status of the transistor just because small signal overreads on that. Is that clear? Last time someone was asking if small VGS changes, what will happen? That is our assumption, that in the range in which I am looking for small signal or plus minus dx as the word I use and not x, then I say in that range the x0 remains as if constant at around x0, and therefore currents are only proportional to DC. In the case of diffam, for example, I said if you have small VG, VGS1, VGS2, it is essentially VGS1 plus VGS1, this is VGS2 plus VGS2, and if the transistor is biased to ISS by 2 on this side, then VGS1 is equal to VGS2. Okay, so DC is essentially the capital VGS, the signals are small VGS1, VGS2, which with difference we call VID, and some average of the two we call common mode. So don't get confused every now and then that small signal to large signal, unless stated otherwise. This is nothing to do with this circuit. Any circuit, for example, the AC value does not change the bias point. That's the assumption we are making actually. Is that clear? That the AC values are small enough and therefore they do not change the DC operating points. Okay, that is how we solve all our circuits. If that also keeps changing, then there is no question of then the signal analysis will call at large signals. That means signal is varying large enough all around and maybe linear or non-linear, we don't care. Okay, then we will solve accordingly. But when I solve a small signal circuit, I essentially say DC operating point is fixed, around which AC signals are superimposed and therefore do not change the operating points. Is that clear? This fact, because last time some query came, so I thought once for all be clear to you that there is nothing called small signal varying the DC operating point. Okay, so the ISS by 2 remains as the DC values. Is that okay? Okay, this is general, this is nothing to do with what we were doing last time, but just to tell you that in future don't get confused between the two words. And for example, just for the making that point clear, and you need not write all of it here because this is just copied from Smith's book. This is just because that day there was an issue, so I thought maybe I will discuss large signal operation. For the diffam which we discussed last time, we say VGS1 minus VGS2, and someone asks how is equal to VG1 minus VG2. Yeah, it does mean essentially saying that source is at the same potential, so the difference of VG and VGS is same. I mean they will be same. In choice of biasing we assured, that is ISS was so guaranteed by us that both transistors are on, are in saturation. Then we write two currents IDS1. If you have the circuit diagram, maybe I can quickly show you, I already shown you. This is ISS, this is minus VSS if needed. this is RD, this is RD, this is my VO1, this is my VO2, okay, this is my VGS1, this is my, or VG2 you can, okay, VG2 or VG1. This is what the circuit I am talking about as of now. This is a typical diffam which is shown here, which you have a circuit already on your paper. So I calculate, assume right now lambdas are zeros. I told you already, if you add a lambda term, what creates the problem? The current becomes non-linear because there will be a VDS term will start appearing in the other side, 1 plus lambda VDS, then it is a non-linear equation and numerically can only be solved, okay. Otherwise analytically, I am not saying it is impossible, you can linearize the non-linear terms, but how much to linearize also is a game. So right now assume that lambdas are zeros as far as analytical calculations are concerned. We will use lambda not 0 for what purpose? For every other purpose I may say lambda 0, but for one thing I will not assume lambda 0, for calculation of R0, because 1 upon lambda ID is essentially R0, otherwise I am saying R0 infinite, okay, which is not really true, R0 is finite, okay. All other things assume lambdas are small enough and can be 1 plus lambda VDS term is 1. So I get the currents in the two arms, IDS1 and IDS2, write the equations as they are, then I take a under root of this, IDS1 under root of IDS2, so I get beta n dash by W by L, beta n dash by W by L, VGS minus VT, VGS2 minus VT, okay. Thus under root of the two saturation currents of the two arms of the M1 and M2, okay. This is for M1, this is for M2, okay. So why I am trying to do it? I am trying to do some maths on doing this. I want to get some this value related to VGS ones. I already made an assumption that already said that VID is VGS1 minus VGS2 or equal to VG1 minus VG2. So I am trying to go back to that value. Is that clear? I just make under root of both the currents and got these expressions. However, I already said VGS1 minus VGS2 is VID because we already said DC values are equal. All that is saying is AC signals. So this is still small signal VID. Is that clear? This is still small signal. DC is cancelling. Okay. So IDS1 minus IDS2 is beta n dash W by VID. However, we know the net current is ISS. So IDS1 plus IDS2 is ISS. Squaring. Now this term I square, so I get beta n by 2, W by L introduce inside beta n dash into VID square. I expand this, so I get IDS1 plus IDS2 minus 2 IDS1 IDS2 square of this expansion, which is beta n by 2 into VID square, but this sum of IDS1 and IDS2 is ISS. So I substitute ISS minus 2 IDS1 IDS2 under root of that is equal to beta n VID square. Why I am trying to do it? In a second it will be visible when I show this. Please note down what I say. I just take the currents, took under roots, subtracted and squared again. Okay, nothing great, no maths worth thinking. Okay, why I do it is the next slide will show you. So if I now substitute, I go back into my IDS1 term and IDS2 term using the expression which I just got, I can prove that IDS1 is ISS by 2 plus minus beta and ISS VID by 2 1 minus VID by square. This is a quadratic equation solving and this is what we did. Okay. So by this I can get this current and this current, IDS1 and IDS2. Did I get the point? I just resubstituted the last equations which I got. I got 2 IDS1, IDS. I can solve this equation now, and using this I can evaluate IDS1 and IDS2 in terms of ISS, beta and VIDs. Two equations I got for IDS1 and IDS2. Now one interesting feature from here you can immediately see. You write these two equations and see what I have, the way I have written them. Okay. If you want in between terms, solve yourself. This is given in Smith book. Okay. So the point I am trying to raise from these two equations is, if VID is 0, what does that mean? VID is 0 means that essentially I am saying common mode we have received. Is that correct? V in 1 is equal to V in 2. So VID is 0. Okay. If VID is 0, that is this term is 0, I get IDS1 is ISS by 2, IDS2 is ISS by 2. Okay. So what does that is essentially saying? When there is a common mode signal, or that means there is no AC signal as if running through, equivalently saying, half the current will go to the M1 and half the current will go to the M2. That's what we started with, and this is provable that half the current moves in the one arm, the half the current goes into the other arm if you are at the same inputs are given, which is obvious. If VGS1 is equal to VGS2, both will draw equal currents, net current is the ISS, so half of current will. So even this equations essentially is trying to tell that they at VID equal to 0, but if VID is much, now why these conditions have been brought? I want to know how much VID I should be allowed for such condition to meet. Okay. Please note down, this is one interesting condition which we got, IDS1 is ISS by 2, when VID is 0. However, each current is ISS by 2, which is ID1 or ID2, which I can write beta n dash by W by L VGS minus VT square, which is beta n VOV square. So I said ISS by beta n, is equal to VOV square. And then I substitute again IDS1, ID2 in this form, okay. So I get VID by 2 B VOV, VID by 2 VOV, VID by 2 B VOV. Just substitute this ISS by beta n equal to VOV square back into same expressions, and you get these two equations. No. For that I got the relationship between VOV, excess voltage, which is a DC excess voltage. Okay, we are now looking for, that's what I keep telling you, don't confuse between ACs and DCs. This is a DC current I am talking about. ISS is a DC current, is a AC part. Okay, so don't confuse every now and then. Okay. So if I now say by these conditions, again we say, earlier we said VID is 0, but even when VID by 2 is VOV, IDS1 is IDS2 is ISS by 2, that means even if VID is equal to VOV, under this equation is 1, you have a relationship with IDS1, that means again DC currents will flow. Okay. Now this essentially what I did, in case VID by 2 is much smaller than VOV, that is capital VGS minus VT, please remember capital VGS minus VT is the DC value, is that clear? If VID, which is your AC signal, is much smaller than VOV, then you can expand that expression, and ISS by 2 ISS by VOV into VID, IDS2 is this. Since this contains AC plus DC, small AC current is proportional to VID. Is that point clear? So under what condition linearity was held for AC? That the small signal VID must be much smaller than capital VGS minus VT. Is that point clear? The day one I started with you an expression, this is the condition. As long as you are in the dx range, linearity is held. Is that correct? If you increase it, because the curve is non-linear, one cannot guarantee that linear expressions can be used, but the condition is, if you have a dx variation, which is VID is a small AC signal, which is much smaller than the DC value, then we say the AC currents are proportional to the difference signal. So whenever you bias by ISS, such that at half the currents flow, that is M1, M2 are identical, RD is identical, biases will be same, at that condition ID small AC currents will be proportional to difference signal. This is what, so condition under which this was true, when VID is much smaller than the DC difference. Is that clear? This issue is very important. Again, why VIDs are not very large, because even with the large signal we got, the conditions can only be linearized when we say VIDs are much smaller than VOVs. That means the AC signals are much smaller than DC values at which you are biasing. Is that clear? This fact we did in bipolar earlier, MOS earlier. Small signal word we say small signal is a condition in which linearity is maintained. Why we are looking linearity? Because for an amplifier, any common source, common emit, any kind of amplifier, what is the thing we always say? Gain is constant. That is, GM is constant, and to do this we must have linearity. Is that clear? To make it linear, condition must be met. Is that clear to you? So this is not really the solving part, or this is not that we need to do this. This is just to prove my point that you cannot have large signals with linear zones. Is that clear? As the first slide shows, if you swing your signal from here to here, you cannot say they are linear. The slope is varying all through. Okay, slope is varying all through. So in such cases, outputs will be proportionately nonlinear terms will appear, and whatever term you wish you can pick up from them, but essentially no linearity can be guaranteed. Is that clear? This issue is what makes interesting all AC analysis away from the DC analysis. Okay. Yes. See, the total AC currents are much smaller compared to DC currents. That is what I am keep on telling, that variation there is a small enough to neglect. The net current will be only the DC current. Is that clear to you? Because the average value, the way it is, 1 plus 1 minus average is 0, and net current at any given average time is only ISS. Is that correct? This is the way it is calculated. Instantaneous current, yes, ISS plus small I, but average current is always ISS. This is the net current, AC plus DC. Subtract DC currents is the small AC current. AC current is proportional to AC difference signal, which means linearity is guaranteed for this region. And to do this, you are meeting that the AC signal difference must be much smaller than the DC difference voltage. Is that condition clear? Essentially saying Vt is very small, so essentially saying VGS should be much larger than the input signals. Is that correct? VGS, which is biasing the transistor, capital VGS, should be much larger than the signal which you are actually amplifying. Is that clear? That is why amplifiers are small signal amplifiers. Is that clear? They are called small signal amplifiers. Yes. Yeah, VOV will matter. Where it will shift, the idea is that in this region where VGS minus VT is holding, the linearity is holding. That is how we started with this assumption. If that the curve goes away, essentially what you are saying is true. But any point wherever I fix it, around that I can assume linearity. Is that correct? But if that signal expands, then I am not sure whether it is linear or not. Any point on that, around that, small signal will always look as if linearity is holding, even if it is non-linear as far as the total curve is concerned. Any DC point, is that clear? As long as you are in saturation, any point, as long as this value is higher than the signal you are using, linearity for that region is holding for you. Obviously, that condition, the day when we started, all transistors are in saturation. Is that clear? Okay, so our interest, as I keep saying you, is not that we are not interested in large signal amplifiers. Some other amplifiers later we may see if time permitting, they are called large signal amplifiers. They may operate in class B or class C or class AB operations, but today we are only looking for class A operations. So we want to now do a small signal analysis of a differential amplifier. A typical DIFAM, as we already have discussed, has two transistor M1, M2 whose sources are connected and they are given a source current of ISS. Okay. Right now I am assuming RDs are equal, but in reality this is not a compulsory condition. They can be RD1 and RD2 as well, but for the simplicity I am assuming the load voltages on both sides are equal. Please remember, this is not a compulsory condition. Okay. but much easier to solve. You can solve without that and you will get nothing great will happen even if they are separate. Now here is the method. I give you two methods to solve. Okay. The first method is called method of superposition. Okay. So there are certain things in which, please look at the outputs of those two are VO1 and VO2. Please look at it. This is V in 1 and V in 2 are the inputs. VO1 and VO2 are the outputs at the two drains of M1 and M2s. Okay. Now we say the method of superposition, what does it say? Assume V in 2 does not exist or V in 2 is 0 and get VO1 VO2 value with reference to input of V in 1. Okay. Then say V in 1 does not exist and say if V in 2 exists, then what is VO1 VO2 and add the two. Is that correct? This is called method of superposition. So we start with this condition. I have already given you steps. Steps 1, set Vg2 V into to 0. This is the first. For superposition I say once input signal is reduced to 0. So we only take AC equivalent circuit, DC part right now we forget, ISS we just ground later. Now if we say we only take AC equivalent circuit and we say this terminal is grounded, please remember this circuit is now shown here with ISS not there. Okay. This is an AC circuit, no DC values are shown there. Okay. This is V in 1, this is your VO2, this is your VO1. Let's call this point Vx and Vy because many books call Vx Vy, so I thought maybe if you read per se any book which has a node X and Y written here, you may as well use this. I am not sure which book, but maybe one of the book because we normally use Vx Vy, so I thought maybe you might have. Okay, so this is your M1. This M2 transistor, please remember from here this is DC, so we go here and this V in 2 is grounded. Is that point clear? M2 gate is grounded, M2 gate is grounded. Is that clear? M2 gate is grounded, V in 2 is 0. Okay. Then you have RD and this is your VO2. Is that okay? Remove DC part. This circuit will show you this is grounded. This is just to show you how it can be slightly tilted, nothing great. Okay. Please remember if there is no DC value, there is no currents anywhere. Is that correct? Is that point clear? DC is, unless there is a biasing, there is nothing can happen. Okay. But I said I am only looking for AC equivalents. Okay. So I am removing DC part for solving. Okay. Now I can see from here very interestingly, I want to find VO1 and VO2 with reference to input of V in 1. This is what my step 2, which is what I am looking for. That means I want VO2 V in terms of V in 1. So the next step we observed that if you see carefully, you see only this amplifier first, RD M1 input V in 1. What M2 is doing for it? Where M2 is connected to M1s? At the source of M1. So essentially if there is an equivalent resistor of M2 seen here, how will it act like? It is a source resistance degeneration of common source amplifier with source degenerated. Is that clear? So I then say, okay, why not I evaluate equivalent resistance here, okay, for M2 and then say, okay, I have one amplifier with source degeneration, okay. This is the trick I use. Is that point clear? This M2 is seeing some resistance for this M1, okay. I want to know how much is that resistance, which I will call source resistance of M1, and if I know that, then I say okay, ये तो common and source amplifier है, degenerated है, क्या gain होगा उसका roughly? Yes, RD by RS equivalently is the gain of a common source amplifier with source degeneration. Is that correct? Or essentially GMRD upon 1 plus GMRS is the gain for these amplifiers. Is that clear? So we will just calculate these things. This is not given in SEDRA, this is mine. So don't think that will be exactly there. How do I calculate this resistance. This is a method which I repeatedly tell you, but I repeat this time once and next time I will never use it. Okay, I will show you right now how to evaluate the source resistance seen by M1. Okay. Yeah, because M2 is still as source to that. Instead of this RD, I will use RD2 there. Okay, just see my equivalent circuit and you will find. This one? No. I am not saying it's a AC ground there. The reason why I am not calling because there is a voltage here right now which I don't know how much is that. Because of signal I am getting a signal voltage here. There is an AC signal going on there, that cannot be grounded. There is a current flow, there is a resistance drop, so there is a drop going on. So I cannot call it ground there. Okay. But this is a DC current. So what path? Infinite resistance. Is that clear? So your point of view is even if it is taken, it doesn't hurt me. No current in that arm. Okay. Okay, please look at it. This is for my M2 I am doing. This is essentially I am doing for M2. The gate as is grounded. Please look at the M2 with gate grounded, common gate. Okay. Let us say between gate and source there is a potential V1. Between gate and source there is a potential V1 shown like this. Corresponding to the output of that will be at the drain source side GM2 V1, GMB V1, shunting R0. This is the equivalent of a transistor. Is that okay? This is the equivalent of a transistor. You may use GMB or you may not use GMB. Okay. R0. And finally, from the drain of that, is the man clear? The resistance RD is not connected to the source but to the ground. Is that correct? RD is AC ground at the VDD. Okay. So this is the ground at the VDD. Okay. Please remember RD is not connected here. RD is connected to the from the upper side to the ground. R0 is between drain and source, but RD is not between drain and source because source is not grounded. Is that clear? So if you now say I apply a potential Vx at the source, okay, and say Ix is the current which is entering here. What is Vx? How do I find resistances? I apply a voltage source, okay, and find what is the current flowing out of it. So Vx by Ix is the resistance seen at this terminal. Is that clear? So I apply Vx Ix. And the net current out of this should be same as Ix because there is only, this is the loop. Where is the loop? Please remember loop is completed through this path. That is why it was grounded. Is that clear? Is that clear? Since Ix is moving and this is open circuit, so no current can go in this side, only current can go through this and finally comes out at Ix and flows. So I write now for this loop equation, IXRD is this drop plus Ix minus this current, Ix is this current minus this current, Gm plus GMB times Vx. Now only thing you have to understand, Vx from this terminal and this terminal is ground. Please look at it, this terminal and this terminal is ground. So between these two terminals, what is V1 value? Minus Vx. Is that clear? This is again what I say you is this loop is now connected. This V1 is nothing but minus Vx. So Vx is minus V1 and therefore the current through I is this is IXRD times Ix minus Gm plus GMB Vx into R0. Essentially what I am saying, current through R0 is Ix plus these two currents times V1. So this is that current through R0. I repeat, I just showed you this current is through R0 plus drop across this plus drop across this is your Vx. Please look at it, this voltage is drop across this plus drop across this. Drop across this is IXRD. Okay, so this is IXRD. Drop across R0, the current through R0 is Ix minus these two currents Gm plus GMB times V1, which is like this into Vx. substitute that here and solve for this expression. So Vx by Rx is Rd plus R0, just solve this. How much is the value I suggested you this Rs should come is this R source of M1 just makes from Vx by Ix will get you Rd plus R0 upon 1 plus Gm2 plus Gmb R0. इस इक्वेशन से Vx by Ix का ये Vx यहाँ भी है, यहाँ भी Vx है, okay. Solve equations. So Vx by Ix will be equal to Rd by R0 1 plus Gm2 plus Gmb into R0. Is that okay? What is this value? This is the source resistance as seen by M1. Is that okay? This is the source resistance as seen by M1. So if I get my R source for M1, थोड़ा सा एक एक्सप्रेशन मॉडिफाई करके देख लेते हैं, इसको थोड़ा सा इसी इक्वेशन को घुमाया मैंने, Rd प्लस R0 अपॉन Gm2 प्लस Gmp प्लस 1 अपॉन Gm2 प्लस Gmb, ये सेम एक्सप्रेशन है, थोड़ा स्प्लिट किया मैंने उसको, ओके. Normally Rd is how much? Tell you how much typical values of Rds will be, I said you many days, 10k to 40k, okay, not more. How much will be R0 typically? 100k to tens of mega ohms depending on lambda and Id, okay. So typically Rd by R0s are very small, Rd by R0s are very small. So this first term is relatively small, is that correct? Rd by R0 is small enough compared to Gm2 by Gmb. So we say this term is neglected. So we say Gm2 by Gmb, and let us say Gmb is also very small compared to Gm2, then it is source is only 1 upon Gm2. तो अभी एक लाइफ लॉन्ग के लिए है, जब भी आपको you will see a common gate and from the source side you want to have impedance of that, it is nothing but 1 upon Gm. The resistance seen by a common gate transistors to the other end is only 1 upon Gm. Is that clear? The full value I have already given, but general values will be Rds will be much smaller than R0 and Gmbs will be smaller than Gm. So we say it is nothing but 1 upon Gm2. This is your circuit now. Oh, I am looking only for transistor M2. Is that correct? This transistor I am looking for, equivalent of. So this circuit, please remember, for this resistance seen is coming from here. Is that correct? So if you use that, then my expression is, this is the gate which is grounded for M2, okay. This is my source where I am applying a source voltage Vx, okay. Correspondingly transistor will have Gm2 V1 and Gmb V1 as the current sources at the drain source side, shunted by R0, and this Rd is going to the ground through VDD, okay. And then I calculate, solve the equations, Kirchhoff law, nothing great in that, and get the value of Rd by Gm Vx by Ix, and that is the value which I am interested in. Just for the heck of it, Gmb is the value of transconductance appearing because of the substrate bias, okay, or because of the substrate bias. Is that clear? Gmb may be present if there is substrate bias, Gmb may not be present if there is no substrate bias. In general we put it, if there is no substrate bias, that is between the bulk and the source, if there is a bias minus reverse bias, then there is a additional depletion charge appearing because of that. That will change VTs and their corresponding value changes Gm. Is that correct? Okay. In our case, gate was grounded, okay, and because of that through the drain it was getting grounded finally, okay. So because of that, that was shown. You can use VGS as the value and which will come V1 later as the term will, because this value is nothing but the value which you are looking, which is VGS, okay. Okay, so I got this view. So is that okay? Please remember the equivalent circuit of my diaphragm on the left side with V in 1 is now Rd with a source resistance of 1 upon Gm2. इसका गेन कितना होगा? RD by 1 upon GM1 plus 1 upon GM2. Essentially it is minus GMRD upon 1 plus GM1 RS, which can be also written like this. Okay. Now what is the one सुपरपोजिशन से एक वोल्टेज निकाला मैंने कितना VO1. Now I also need to calculate VO2. Now we can say that M2, start looking the circuit again. M2 ये जो ट्रांजिस्टर है M1 जिसके ऊपर इनपुट है, ये एज इफ आउटपुट तो यहाँ पर से इसका जो आउटपुट है सोर्स का वही उसको इनपुट पे जा रहा है. Please remember the game I am talking. The M2 transistor now sees as if it is driven by a source follower of M1. Okay. Okay. I repeat, now we can say that M2 is driven by M1 as source follower, and how you check. If not, I will explain you like next time. If that is so, I may say I have an M2 whose gate is grounded, RD which has a VO2, and it is driven from M1 side of a source resistance of RTV and a source voltage of Thevenin's voltage source of VTV, and that means M1 का इक्वलेंट जो है उस सोर्स को कितना वोल्टेज और कितना इक्वलेंट रेजिस्टेंस दिखाएगा M2 के लिए is the Thevenin's equivalent for this. Okay. Clearly we can say VT1 is nothing but V in 1 because that is the input available to you, and RT1 is nothing but 1 upon GM of M1, parallel R0, but R0s are much smaller, so neglected. So if I now find out for this VO2, please do it again yourself. I repeat, this is as if the M1 is represented by now equivalent of voltage source, Thevenin source plus its Thevenin's resistance. The Thevenin source for source follower will be same as input, which is V in 1, and the resistance will be essentially 1 upon GM of that transistor. Remember, parallel RO1 will appear here, but that RO1 is higher, so we forget. So VO2 by VO2 is, as far as this is concerned, GM2, maybe you can call it RO2, but RO2 is RO1, we are going to say later. ये सादा एम्पलीफायर का गेन निकाला मैंने VO2 by V in 1. If I do some mischief correctly, I would say this is also equal to 1 upon GM1 plus 1 upon GM2. Represent RS by 1 upon GM1. This is 1 upon GM2. ROs are much higher. Divide by GM2 ROs everywhere. Please remember, divide by GM2 RO2 on the denominator and collect the terms. Smaller terms neglect kiya. So this is RD upon this. So what is this gain? At the second terminal, but with reference to input at M1, VO2 at reference to V in 1. Earlier what we calculate? VO1 by V in 1. So the difference gain is how much? What do we call difference gain? The VO1 minus VO2 divided by V in 1 is the difference gain. Same currents are, same voltages are, this is plus, minus of minus will be just double of that, minus 2. Please remember, same value has come there for VO1 with a minus sign. Okay. So minus of minus, twice minus, so minus 2RD upon this. If you say GM1 is equal to GM2 is equal to GM, then this is nothing but minus GMRD. Normal common source amplifier का gain कितना होता है? Minus GMRD. So different gain भी कितना हुआ? GMRD. Is that correct? Different का gain भी same amplifier जितना आया GMRD. But this is on the what is the step right now used? Only using V in 1. So that means V in 1 के लिए same equivalent gain आता है GMRD. Minus sign. Why minus? Opposite of that. Okay. Can we say now same thing can be repeated for V in 2? Identical situations. Okay. So how much we can get for that? VO2 minus VO1 will be similar value. Okay. And then the net gain will be how much? subtract करोगे तो 2 GM minus 2 GM RD will be the gain of a difference amplifier. Calculate VO2 by VO1 or VO1 minus VO2 by the same technique for the other arm now. Okay, इसको ground करो, इसको वो का वही, यही gain वापस आ जाएगा. Add करेंगे तो it will become 2 GM RD. This is one method. This is not the best method. अभी मैं एक जो method आपको दिखा रहा हूँ वो quick है, correct है कि नहीं ये आपको verify करना है. But otherwise it will give you very quick results. But there are conditions to do this. Okay. This method is called half circuit analysis. ये आपको please remember this is very few people give it. I am not sure, just check with her. So I might have given in the appendix as well. You have a lemma here. A typical circuit is shown here, okay, which is called symmetric circuit. Please remember this is not necessarily given in Cedra Smith, but may be given as. I have two devices D1 and D2 shown here. For example, this is my D1, this is my D2, okay. 3 terminal devices which receives inputs V in 1 and V in 2, has I1 I2 currents, and the net current is of course I1 plus I2 is IT. Now this symmetric circuit has something condition we are now putting, and that is very important. Let us say there is an equilibrium value of V in 1 called V0, not output. Please remember I am not talking of output. Output is V0 is the equilibrium value, average value, and V in 1 changes. Essentially what I am saying, if this is your average value V0, sorry, the Vin changes by either delta Vin or by minus delta Vin. Is that correct? This delta word is a small, that has to be understood. Vn value has the average value of V0, at times it goes plus delta Vn, at times it goes to be, there are only two values therefore it can take, V0 minus delta Vn or V0 plus delta Vn as the two values it can pick up, okay. Please remember the game is this, condition in symmetric circuit is this is what diffam allows, okay. If there is a change in this by delta Vn, the change in Vn2 is minus delta Vn. Is that point clear? If one input rises by some small value, the second input must go. Why this condition has to be made? Vn1 plus Vn2 by 2 is common mode and Vn1 minus Vn2 should be same. If these difference and common mode signal have to remain same, any change here must be opposite change in the, this is called symmetric circuit. Is that point clear? Change in V in 1, if it is plus, change V in 2 will be equivalently minus. Change in V in 1 is negative, then change in V in 2 is positive. They go always, so that the sum total is always equal. If you subtract from them, both will cancel and you will only get V in 1 minus V in 2 constant. Is that point clear? V in 1 minus V in 2 is always constant, you increase it, decrease it, the difference will always get cancelled, okay. Then by this lemma says, if the circuit still remains linear, that is GM's constant, then the potential at this point P, node point P, does not change. Is that point clear? The potential at this node P remains Vp. We will solve this problem which you are asking, okay. I repeat, if there is a 3 terminal device which receives signal, which is if this increases, this decreases, this increases, this decreases by same amount, then this voltage does not change, okay. This is what lemma is all about. Now we will show you the lemma proof, okay. Equivalently saying, if there is a Thevenin's equivalent resistance of D1 side is Vt1 and Rt1 is resistance. This is node P for you which has a potential Vp. This is Vt2 Rt2 for the M2 side, and let us say I is the current flowing from this side to this side. We also assume RT1 is equal to RT2 for simplicity, we can prove otherwise, but just to show you here, I write Vp is this voltage minus drop across this, and this voltage is ITR2 minus this, minus V2. I sum this two equations, 2 Vp is Vt1 minus Vt2 if Rt1 is equal to Rt2. But we also know Vt1 minus Vt2 is Vid, which is Vid by 2 is equal to Vp. Now you can see from here what did I do? Vt1 plus delta Vt minus of Vt2 minus delta Vt. एक पड़ा एक कम हुआ. The first Vn1 increases by delta Vt, the other one decreases by delta Vt. The difference between the two is Vt1 changes from Vt1 plus delta Vt, Vt2 changes Vt2 minus delta Vt, delta Vt will Vt1 minus Vt2 will remain, and okay. So what is this point I am trying to say? If this circuit is symmetric, and this word is symmetric is now shown here, and that is what essentially means. You look at your diffam, for AC, on your left and on your right you have a symmetric circuit, is that clear? So I can break that point. I can say I have two circuits independent, one on this side, one on this side, and each source as if for AC is grounded as if, then I can solve gain for this, and then I say okay, if I get Vx Vy for this, I can always get Vx minus Vy by Vgs. This is called half circuit analysis. What is the condition I told you? Circuit should be symmetric, okay, some way, that is mirror of this, it should be mirror of this, okay. If that is so, you can break the circuit, and if you can break the circuit, I can independently solve the two circuits, okay. That means Vp is constant. Symmetry is only possible if Vp is constant, okay, that is what I meant, okay. If that is so, for this transistor, please remember this is VGS1. Now condition is, please remember the first case VGS1, what is VGS2 will be, that's for symmetry, minus VGS1, that is a condition you must meet, okay. If that is so, Vx by VGS1 is minus GM1 RD parallel RO1, Vy by minus VGS1 is minus GM2 RD parallel RO2, GM RD, okay, RO is parallel to RD, so RO1 RO2. So Vx minus Vy upon 2 VGS1 is equal to minus half G1 RD plus sum of the two, okay. Why I am using this 2 both side, can you think? इसका 2 आने वाला है ना, if they are equal then that 2 will appear, 2 GM RO RD RO will appear, so 2 I want to cancel from there, okay, just that tricks. So I get, if I say GM1 is equal to GM2 is equal to GM, RO1 equal to RO2 and RDs are same, then this become 2 GM RD parallel RO, 2 cancels, so minus GM RO parallel RD, which is Vx minus Vi upon 2 VGS1, okay, or to say which is nothing but Vx minus Vy is VGS1 minus VGS2, which is nothing but, please remember 2 VGS1 can be written as VGS1 minus VGS2 because VGS2 is minus VGS1, so 2 VGS, is that clear? How did I get these are equal? Because I say VGS1 is minus VGS2, okay. So I wrote VGS1 plus VGS1 and the second VGS1 I wrote as minus VGS2. So it is VGS1 minus, but this is nothing but your difference signal, is that correct? This is nothing but your difference voltage. Vx minus Vy is the output, difference output. So this is the gain of a diffam. How much is that gain? Minus Gm times RO parallel RD, and if ROs are larger then it is minus GM RD. वही रिजल्ट लाके दिखाया आपको मैंने, is that correct? This is called half circuit analysis. Similar thing we can do for Now the question is, which is many people ask me, so I normally show you, समझो symmetry नहीं है, ये एक example देखो, then you will appreciate what I said. Let us say V in 1 is not equal to V in 2, that by minus sign or whatever it is, okay. Okay, so here is the condition. If you say V in 1 is not equal to V in 2 as such what you thought earlier, I can now play interesting game. This V in 1 is broken into two voltage sources, V in 1 by 2 and V in 1 by 2. प्लस माइनस सीरीज कनेक्टेड है, तो ये दोनों मिलके V in 1 ही है. Then I can put two other sources in of V in 2, but now in half opposite polarity, plus and minus. Is that clear? That means no source. V in 2 is no source, but I still put it plus V in 2 and minus V in 2 by 2. Okay. Same thing I play in this side. V in 2 by 2, V in 2 आधा आधा किया और V in 1 का प्लस माइनस किया half. Is that clear? ट्रिक समझ में आया? ठीक है, आपने बोला सेम नहीं है मत करो ना. सो इसको हाफ किया, इसको हाफ V in 2 को लाया बट अपोजिट रखा, इसको V in 2 को हाफ किया, इनका V in 1 का हाफ अपोजिट में लगाया. Do you think something is visible from here if you see this circuit? I can now say V in 1 minus V in 2 by 2. क्या सिग्नल मिलेगा आपको? This minus this, VRD by 2. ये दोनों सम हो जाएंगे तो क्या मिलेगा? V in 1 plus V in 2 by 2. Okay. इसका मतलब ये है, these four voltage sources are actually not changing anything what is given here. Is that point clear? Just divide half. एक को सेम सीरीज में रखो, एक को अपोजिट रखो, and they are same now. But using this, I can now make a fun of this circuit and I can solve independently now. This is equivalently saying there is a voltage source of V in 1 minus V in 2 by 2, V in 1 plus, same argument is opposite side V in 2 minus V in by 2 and V in 1 plus V in 2 by 2. इसको भी थोड़ा सा गेम खेला है मैंने. ये डिफरेंस है, ये भी माइनस ऑफ, look at V in 1 minus V in 2 with a minus sign, V in 1 minus V in 2 with a plus sign, okay. And since this V in 1 plus V in 2 is common to both, I connected them here and put it down. अब इस आर्म के लिए भी है और इस आर्म के लिए भी है. Can you now see this is VID by 2 and this is minus VID by 2. So डिफाइन का रिक्वायरमेंट हमने अभी भी मीट कर दिया आपके लिए. This is VID by 2, this is minus VID. आपने कहा था they are not equal, I still made it some way look as if they are defined inputs. But what is additional term appeared? The common mode term appeared now, okay, common mode term appeared now, okay. Or to say, if you have drawn the circuit, don't think too much, these are just some of the two are same as V in 1 and V in 2, no difference whatsoever, okay. So now we say, please remember, I can rewrite saying V in 1 is V in 1 minus V in 2 and plus V in by 2 and V in 2 is this. So this is my difference signal, this is my common mode signal. अब क्या कर सकते हैं? अब हम डिफरेंस सिग्नल के लिए गेन निकालेंगे और सुपरपोजिशन कर देंगे, कॉमन मोड के लिए गेन निकाल देंगे और फिर गेन को सम कर देंगे. इज दैट मेथड क्लियर? आई हैव टू सिग्नल्स, difference mode signal, common mode signal. I will find the gain for both signals by and add them by superpositions. Okay. If I do so, I get V0 is Vx minus Vy, which is V1 minus Vo2, which is the difference signal is V in 1 minus V in 2. Then V0 by Vid is half Gn parallel है ये, वो जो पहले लिखा वो expression. Okay. And if Gm1 is Gm2 equal to Gm R01 R02, Vo by Vid is Gm Rd parallel R0, which is my difference gain. Is that correct? Which is my difference gain. If the source is ideal, the current source is ideal, what is the common mode says actually? Common mode means signals are same at both ends, is that correct? So VO1 will be equal to VO2, so difference of VO1 VO2 will be 0. So what is ACM, common mode gain? 0, because VO1 minus VO2 will be always 0 if V in 1 equal to V in 2, is that clear? If the inputs are same and the transistor is circuit is symmetric, both outputs will be same, that means if outputs are same then difference is 0, so ACM is 0. So what is the gain finally you got U1 using when the condition was not made? Minus GMRD. So it is not compulsory that they should be that way, even if they are not equal kinds, they can be made equal kinds. What does that essentially means? In case ACM is not 0, then the net gain may not be same, is that clear? In this condition we assume that the source is ideal, the resistance across current source is infinite, okay. Is that clear? DC current is flowing but AC is, RE is as if is infinite, okay. If not, then there will be some potential will appear there and that will modify, and then the ACM may be positive, and then you will have to actually get the gain of AVM, DM plus CM as well, is that correct? For ideal difference mode signals, whether equal or not, still can be same GMRD, okay. But for non-ideal, what is the term which will case when it is non-ideal case? What is the term we are looking for? I want to know what is the ACM value with reference to ADM, how much it is, whether ACM is 0, then I would say the ratio of ADM by ACM is infinite, okay. This is called common mode rejection ratio. Ideally common mode rejection ratio is infinite, okay. What does that means? At no common signal will be transferred, only different signal will be amplified, is that clear? However, in reality if ACM is finite, the CMRR will be not infinite but maybe 10 to the power 3, 4 or something, 80 dB, 100 dB or 120 dB kinds, okay. Now we want to find if ACM exists, how much is the real value now, okay. If the current source ISS is not ideal, what does that mean? Not ideal means, what is ideal current source? The shunting resistance is not infinite but finite, okay. Non-ideal means RSS across the source is not infinite, okay. अच्छा current source किसको बोलते हैं, उसका output impedance is infinite, okay, but it is not true. In that case, now look at for the common mode what is happening. V in CM, which is equal to V in 1 equal to V in 2, due to symmetry Vx Vy is Vo1 minus Vo2, so Vx minus Vy is Vo1 minus Vo2. Please look at it the way I am now doing. These voltages are same, so I connect. You said no, Vx is equal to Vy, so I connect. Same potential है ना, आपने बोला ना symmetry है, Vx is same as Vy, symmetric circuit है. Vx is Vy, signals are same, symmetric, outputs are same, difference may be 0, but difference is 0, yeah, by shorting I am making Vx minus Vy is 0, is that clear? Difference between Vx and Vy is 0, so I short them, okay. I have common signal to both gates V in CM and there is an RSS. Now if you look at this circuit carefully, these two transistors, how do they look to you? Please look at the circuit. One transistor is this, the other transistor is this, both are getting same input, drains are connected, source are connected. क्या ऐसा दो ट्रांजिस्टर यदि पैरेलल में है, सॉरी, क्या इसका इक्विवेलेंट बता सकते हैं क्या होगा? दिस इज से M1 एंड M2, इसका इक्विवेलेंट रेजिस्टर ट्रांजिस्टर होगा M1 प्लस M2, उसमें क्या इक्विवेलेंट होगा? हाउ इज वी राइट करंट फॉर ईच? लेट्स से लीनियर और एनी बीटा n into W by L. everything else is common. So if I add the current passing through this plus current passing through this, what is the total net current? Twice, which is equivalently saying the transistor equivalent current is twice the width of that one transistor. Is that point clear? If you have a transistor of 2W instead of 1W, this is 1W, this is 1W, each is carrying equal currents. Together we may say you have one transistor which has twice the widths. Is that correct? So we say an M1 and assuming VTs are same, everything else is same, betas are same, then we say it is only twice the widths. Okay. So the transistor has twice the width. Is that clear? This is called equivalent transistor. What is it called? Equivalent transistors in parallel. Two transistors are in parallel, their width sums. Okay. So this is essentially, this circuit then reduces to, okay, can you also see this RDs are also parallel? ये short है, ये भी short है. ऊपर देखिए last RDs भी parallel में हैं. So equivalent resistance is RD by 2. This is RSS which is common. This is transistor which is equivalent of twice the width, called M1 M2 transistor. Okay. Now इसको solve करना तो आसान है. ये मेथड है इसकी, ट्रिक्स की है. अच्छा, आप लोग जो कह रहे थे M1 M2 being in parallel, we say widths are equal, W1 plus W2 is 2W, ISS by 2 is ISS, we have GM equal to this, GM M1 M2 is this, GM1 is GM2 is this, so the GM is 2GM. You wanted to prove, you wanted to say it, so I showed you it is provable also. Write expression for GMs. Please remember, these GMs have been calculated on what basis for each transistor for DFAM? The current is how much? DC current? ISS by 2. Please remember, this is never to be missed. That only makes symmetry, otherwise it does not make any symmetry. Okay. So GM of the new transistor is how much? Twice that of individual, assuming others are all values are equal. Okay. I just showed you, substitute there and you get 2 GM. Is that point clear? Okay. So you have now a common source amplifier with source degenerated by what resistance? RSS. You have a load, how much is load? RD by 2. Source resistance RSS. GM is now 2 GM. Okay. So then VO by VNCM, common mode gain, is minus GM RD upon 1 plus 2 GM RSS. Please remember 2 GM, पुराना GM के twice है वो, 2 GM RSS, which is equal to, essentially if you say GM is divide करें, one is, this is larger than 1, GM cancels, so it is, sorry, RD by 2 RSS, sorry, AVCM, is it now finite? Because RSS is not infinite. So RD by 2 RSS is certainly not 0 or not, not 0, but some finite value. So the common mode gain is now the ratio of the load resistance. Okay. Oh sorry, I also made a mistake. What is the mistake I made? Okay. So, so you are right. 2 GM into that is correct. Thank you very much. I had some wrong thinking. Okay. So I should write like this. Okay. Okay. So what does that mean? If I want to improve a term which is called CMRR, AVDM by AVCM, which is the ratio of difference gain to the common mode gain, and since it is finite and we want to keep as high as possible, what is the condition I should meet? RD should be small or RSS should be high as much as possible. So जितना अच्छा current source आप create करेंगे उतना common mode rejection ratio higher होगा. Yes. But now it is not the difference output we are looking only for the common mode outputs. but that is what we said, it will get rejected at the end, but not fully. That is what I am trying to say. Each is now VO1 which is not which has a finite value in fact, that is what we are saying. Okay. Otherwise we would say a common mode would always get rejected independently. Now we say all of it is not rejected, it may be small, but there may be a common mode outputs. Along with what we are saying, difference का VO1 plus उसमें कुछ common mode का भी आ रहा है. Is that point clear? Is that point clear? Which is not neglected now. Perfect. Difference is still same. Is that that is ADM. DM is still independent of what CM is doing it. Is that correct? But earlier we said RSS is infinite, so we are always saying ACM is 0. We say it may not be 0. Yes, this is individual only we calculated equivalently. Is that clear? That is what we say, AVCM is not 0 now, which means there is a finite common mode rejection ratio which may be as high as 100 dB to 125. I do not know how much is 741 you measured. So how many things you monitor for op-amp? Gain, input resistance, output resistance and CMRR. Of course there are a few more PSRR and other, but they are little more higher order. Anyway, we will do op-amp. Op-amp is, DFAM is, what did I say, start day 1? DFAM is the first stage of op-amp. So we are now trying to see, once we understand DFAM, इसका जो output है वो कहाँ देना है मुझे? Gain stage को. Is that correct? And the gain stage I will put it a buffer and then we call it as operational amplifier. So the first input stage of a op-amp is a differential amplifier, and that is what we first looked into. Okay, is that okay? Okay, before we quit, we may do this analysis next time, but this is a very interesting things. In real circuits, a difference amplifier will never have a resistive loads. What is the reason? Why resistances are not used in integrated circuits? Area. So एक resistor ही पूरा chip का area ले लेगा. 40K का resistance may take 2 mm by 1 mm area. So no one is going to put in an op-amp 4 resistor और बाकी कुछ नहीं. So we will always use transistors as resistors. Okay. So here is the 3 kinds of loads which we use in the case of difference amplifier and therefore op-amps. ये तो आपका नॉर्मल डिफरेंस है. ये जो नीचे आपको दिखा रहा हूँ मैं M5. What is M5 is giving when I am giving a VGG voltage, which is some voltage I adjust. What is this M5 connect? This will give me current source. So I can fix the current source by adjusting VGG. Is that correct? I can fix the current source by adjusting VGG. There are 2 transistors M3 and M4. There are 2 transistors for M1, M2 they shown here, M3 and M4. These are all N channels as of now, but they can be P channels. Some connection will be modified when we say. Both are N channel devices. The gates are common and gates are connected to the drain VDD. What is when I say gate of a N channel transistor is connected to the drain, what is the status of that transistor? Permanently saturated, because VGS is VGD and VDS is same. Okay, therefore VGS minus VT will be always smaller than VDS, come what may. Is that correct? VGS, please remember, this is my VGS, this is my VDS. Since same potential exists across this, so VGS minus VT will be guaranteedly less than VDS. Is that okay? Therefore M3, M4 will be always in saturation. So what is the typical value of such resistors will be? Transistor in saturation resistance ज़्यादा होता है या कम होता है? Device saturate हो रहा है IDV ऐसा, resistance कैसा रहता है? Very large, R0 ना? So it is a large resistor. Of course their value can be adjusted by what? The current which I pass and length W by X are used for M3, M4. Okay, I can change the resistance values. Okay, ओके, दिस इज कॉल्ड नॉर्मल एक्टिव मोड लोड. यदि समझो ये पी चैनल करते तो क्या चेंज करता मैं? इंस्टेड ऑफ एन चैनल then the gate connection should have gone where? Like this. They should go to the source side. Is that correct? They should go to the, ऐसा अलग अलग आपको उसको बोलते हैं डायोड कनेक्ट. नो, डायोड कनेक्शन इज कैन बी कॉल्ड, बट दिस इज व्हाट एसेंशियली इज डायोड कनेक्शन. ओके, दिस इज इफ आई पुट, this is essentially is a diode connection. This is drain, this is source, this is gate for a P channel. Okay, this is called normal active loads. I can also put, instead of directly going to VDD, which is VGG1, and if it is VGG1, अभी एक मैंने M5 का क्या बताया था आपको? If I put a VGG and M5 acts like what? Current source. So M3, M4 acts like current source. Okay, acts like current source. So this is called current source loads. As soon as I put a VGG there and I adjust that value, I can fix the current in M3 and M4. Okay, so I say it is current source loads. Okay, तीसरा क्या होगा? डायोड कनेक्टेड हो गया, करंट सोर्स हो गया. This is called current mirror load. This is the connection which all analog op-amps will use. This is the kind of loads all op-amps use. Okay. Is this connection clear to you? The gate is connected to only one side of the drain. Mirror में क्या करते हैं? Do you recollect mirrors? Let's see our mirror. What did we do in mirror? यदि W by सेम है तो यहाँ I रेफरेंस है तो I0 is I reference. Depends of course, if the W by are there, it will be multiplied. This is current mirror. Is that correct? This current is mirrored to this. As soon as I make this connection, gate going to the drain of this side, I am making it current mirrors now. Okay, currents in this arm and current in this arm are mirrored now. Is that correct? Current in this arm is same as current in this arm, mirrored. Mirror also will have output resistance. So the output resistance of mirror is the equivalent load for M3, M1 and M2. Is that clear? This is the third kind of load which I may use, and almost 90% of op-amp loads are current mirror loads. Is that correct? The only disadvantage of this is it only gives single ended outputs. Is that correct? There is the other terminal is anyway connected to the gate. Okay, so it gives you only single ended outputs. Okay, so it is a DFAM with single ended outputs. Why did I do this? What did I tell you in op-amp? What should be the next stage? There will be a gain stage. How many inputs it will expect from you? One input. Is that correct? So I created a one single ended output out of this. The next stage is going to be a single ended amplifier here, gain stage. I need an input now. Okay, so I created an input out of this. Okay, this is the typical DFAM input, typical DFAM stage, which is the first stage of an op-amp. Yeah, disadvantage is many times I am really looking for difference gains. In this there is no difference gain. Is that correct? Okay, so maybe I will give you a figure which may be interesting to show you. आपको लास्ट टाइम भी मैंने बताया था ओपैम में उसके बड़े फिगर बड़े मज़ेदार रहते हैं. ये दो इनपुट हैं समझिए, तो एक तो यह पॉसिबिलिटी है जो अभी आपको दिखाया, दूसरा पॉसिबिलिटी ऐसा भी है. इज दैट क्लियर? टू इनपुट्स टू आउटपुट्स. ओके, तो अभी जो स्टेज दिखाया वो नहीं दिखा सकते, अभी यही दिखा सकते हैं. Normally in op-amp, unless difference outputs are required, you will prefer this, is that correct? Because in this the gains may not be very high, in this the gains are typically of the order of 10 to the power 4 to 10 to the power 5. Okay. An open loop gain of a diff-amp if the order of op-amp is of the order of 10 to the power 4 or 10 to the power 5, 80 dB to 100 dB gain is available to you, open ended. Why open ended? There is no feedback, open loop है ये. रियल सर्किट कैसे यूज होने वाला है, आपने अभी देखा होगा कि एक इनपुट यहाँ देंगे, इसको ग्राउंड करेंगे और यहाँ से कुछ, दिस इज अंडर फीडबैक नाउ. So we say V0 is minus R2 by R1 times Vn. Now it is independent of what? The op-amp itself. Now this is something interesting. I repeat, I will come back to this circuit. By doing this circuit, the output is or gain is independent of the transistor or op-amp parameters. तो फिर op-amp हटा लो ना. आप ये कहना चाह रहे हैं ये सर्किट नहीं काम करेगा, ये डिवाइडर हो जाएगा. Is that okay now? See you then, we'll meet again.